Okay, well, we started out by letting this thing spin, seeing how fast it slows down. We didn't do an official observation. And then we had a piece of plastic, kind of like this, on it, spun it again, and it appeared that it was slowing down more quickly because of, and I think people pretty much understood that was because of air resistance. Okay, now how are we going to observe that when we observe it in lab? We're going to take some pretty tight observations of this, because there's a lot to be learned. Usually a physics class starts with motion along a straight line. It's easier to understand this. And then parallel to that, we understand motion along a straight line. Also, the big stumbling block for most students, especially students who've had high school physics, comes when we start dealing with rotation and angular momentum and that kind of stuff. That's where all of a sudden you got all these formulas, and formulas don't really help you understand anything. Partly because people have used formulas to solve problems that they don't understand anyway, up to that point. And all of a sudden, you got to not only be able to use formulas, you got to be able to think through problems. So we're going to kind of cut through some of that by getting familiar with some of the aspects of rotation as we talk about motion. The mathematics of this motion and the mathematics of motion along a straight line are identical. You just use different symbols. And we want to kind of get that straight now so that when you see the equations for uniformly accelerated rotational motion, you don't feel like you've all of a sudden been dropped in the middle of a foreign country. Okay. Okay, well, anyhow, now I ask, how far does this rotate between here and here? And I got the answer, well, that was one revolution. And I said, how else can you say that? I said, 360 degrees. And then, okay, there's another way to say it. Yeah, 2 pi, which means 2 pi radians, because the default unit for angle is not the degree, it's the radian. Now, one thing you might want to try to get used to in this course, I don't want to see calculations with degrees that don't have degrees in the units. I want to see degrees when you mean degrees. If you want to say sine of 37 is 0.6, I don't like that, although I more or less tolerate it. But it almost inevitably leads to confusion with units, okay? Because some people be in radian mode, put in sine of 37, and they'll get, what is a sine of 37, 0.6 something. No, that was sine of 37. 37 would be almost 6 revolutions. It'd probably be a 4th quadrant, maybe a 3rd quadrant angle. I don't know. Okay, but it would not be 0.6. All right. So, you know, I want to see units on any angle that's not in radians. If you put down sine of 0.7, means sine of 0.7 radians, not sine of 0.7 degrees. Okay. And that is mathematically what it means. Now, in engineering, you're going to see all kinds of calculations, no units on degrees. Okay. You just know from context you're working in degrees. In this course, sometimes it's degrees, sometimes it's radians. If you're not going to put units on it, it's radians. Okay. Just to keep it straight, I recommend you put degrees on degrees and put radians on radians. Okay. And again, I'll know what you mean. I might not even penalize it, I'll just complain. But you don't want me to complain. Okay. Okay. So anyhow, okay, that was 360 degrees. And I asked, how far did this end travel, given that this whole thing is 2 feet long? Okay. Well, it traveled the circumference of a circle, right? Circle of diameter 2 feet. So that was 2 pi feet. Okay. Or if you wish, circle of radius 1 foot, which is 2 pi times 1 foot, which is 2 pi feet. Okay. So we know how far this moved. If this is at 12 centimeters from the center, how far did it move in that one revolution? Well, 2 pi times 12 centimeters, which is 24 pi centimeters. Okay. Again, you want the units on your answer. Okay. Now, between this one and this one, which one moved further during the revolution? Point, this side or that side? Can you see? Which one moved further? Well, the one that's further from the center, and this is a centimeter or so further from the center than this one, right? So this one moved further, okay? Which one moved faster? The one that moved further in the same time, okay? So everything here is moving through the same angle. Everything moves through 2 pi radians for every degree, right? The things that are closer to the center move further during that 1 radian than things that are closer, okay? So which one has more kinetic energy, the one that moves further or the one that is closer? You know what kinetic energy is. How many of you know the formula for kinetic energy? How many have had high school physics? How many forgot what the formula for kinetic energy is? How many never knew? I'm going to give you a formula, okay? Just, because people love formulas. I don't like to start with formulas. I like to start with concepts. But, formulas express the concepts. And the problem a lot of physics students have is they stop with a formula and never understand the concept that the formula represents. So they get to the exam and they use the wrong formulas that are just ridiculously inappropriate, and go out thinking they did pretty well. So well, by that time, you probably got used to the idea that if all you understand is formulas and all you do is search for formulas, you're not going to get very far. You might scrape out a passing grade, but you're not going to do real well. And you might not even pass. Okay, so anyhow, kinetic energy. One half mv squared. Okay. Now m is just the mass. So if we want to find the kinetic energy of this magnet, m is about 0.05 kilograms. It's just a mass measured in units of mass, which would be the SI unit is kilograms. Okay. So the mass isn't changing. The mass of this one's the same as the mass of this one. Okay. So which one's going to have the greater V? Well, V is its speed. V with an arrow over it is its velocity, that's speed with the direction. And we'll worry about that soon. Okay. But plain old V is just how fast it's moving. So which one is going to have the greater kinetic energy? This one. Okay. If this one is out here twice as far from the center as this one, how many times as much kinetic energy is it going to have? Just hold up fingers. Everybody's saying twice. What happens to V in this equation? It gets squared. So if you square something that's twice as big, how many times bigger is the result? It's 4 times as big. That's the idea of proportionality. Now, I first encountered proportionality in 8th grade. And I've been thinking in terms of proportionality ever since. Proportionality is kind of hard to teach to most students, but to reasonably bright students, it's very easy concept. Now it builds into things that get more complicated, but it's an easy concept, but nobody teaches it to anybody now. Bright students get the shaft in our educational system. Okay, you're going to need to come up to speed in proportionality, which takes about 10 minutes if you concentrate on it. So I'll give you the opportunity to do that later. You have to see proportionalities in these equations. You have to understand that if V is twice as big, then V squared is 4 times as big. If V is 3 times as big, V squared is 9 times as big. You can't look at an equation and begin to understand it if you don't understand that. Okay? What about gravitation? How many of know that gravitation is an inverse square force? I heard that in my earth science class in 9th grade. And I've been pondering it, pondered it, and okay, it's inverse square. Then I learned more. As I learned more, I had more. I had exposure to this idea at the age of 13. If you don't have the exposure to that idea at the age of 13, you're never going to understand it as well as somebody who did. Yeah, given equal aptitude and effort and all that stuff, okay? But it's still pretty easy to understand, okay? So I want to, again, that's an easy one, but I'm going to want you to get over that hurdle, okay? Just, another form, you don't have to remember this. That's an R squared in the denominator, okay? And this represents the force of gravity between 2 masses. So if you got the Earth and the Moon, you know the mass of the Earth, which is about 6 times 10 to the 24th kilograms, and the mass of the Moon, which I think is about 1/80th of that, okay? And the distance between them, which is about 400,000 kilometers, you calculate the force between the Earth and the Moon because there's the distance and there are the 2 masses. And this is just 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared. Everybody got that? Remember that now? Don't worry about it. Okay, we'll talk about it when we get to it. The units are newtons times meters squared divided by kilograms squared, right? Newton is a measure of force. Are you familiar with that? You encountered that? If not, don't worry about it right now, but it's a measure of force. We'll define that later. So your force wants to come out in newtons. Okay. Now, you got 2 masses. What are the units of the masses? It's kilograms and kilograms. That gives you kilograms squared. Okay. So you got kilograms squared up here. If you want to get newtons over here, this G had better have a kilogram squared in the denominator to divide out the kilogram squared in the numerator. And this has units of meters squared, okay? So you better have a meter squared in the units of G. So I say the units are newtons times meters squared, which will divide the meter squared here, divided by kilogram squared, which will divide the kilogram squared here, leaving you newtons. Now this is an inverse square force. What's a graph of an inverse square force look like? Well, if you know precalculus, you know what the graph of the reciprocal square function looks like. But nobody knows precalculus. Okay? So there are, and I'm telling you what you don't know, but I'm also telling you, we're gonna give you the opportunity to know these things, because these are like building blocks. You don't know what a reciprocal square function looks like, okay? Well, my own history, I pretty much would have made perfect score in my math SAT. Had really good math teachers and reasonably smart, not maybe the smartest guy in my high school, but there are a couple of other candidates. My test scores were just a little higher. And I was a mediocre student at a really good school when I transferred, okay? Maybe a little better than mediocre, but not good enough to get in a kind of exclusive calculus class, but not good enough to get in the accelerated calculus class, okay? So, I'm kind of smart, but, nothing spectacular. The reason I didn't make 800 on my SATs was because we didn't have a precalculus course. We had a really good trig course, and we had a really good course in logic, which is more valuable than precalculus would have been ultimately, because I understood proofs. I could understand proofs. I took some doing, but I could understand proofs. And my point, though, is that I didn't know what the inverse square function looked like. So when I saw graphs in my physics book that looked like this, I said, okay, what's that have to do with anything? Well, that's a graph of this, okay? And I couldn't connect them because I hadn't had pre-calculus. The reason I didn't make perfect score in my SAT is I didn't know what f of x meant. I pretty much got everything else, just my score was pretty high. The only reason I think I didn't get a perfect or near perfect score was that, okay? It's a pretty simple idea, but I'd never seen it. And I'd never seen the idea of these functions or talked about how they're constructed. Okay. So I'm going to kind of recommend that you look at some of the stuff I do in my pre-calculus class this week. Just a quick look. I'll probably have some of it saved on the board for next time so I can just show you what I'm doing. But it'll give you a handle on these toolkit functions that are the basis of everything you've done in calculus. Fair enough? It's easy. You're not going to have any trouble with it. Okay. See that for 5 minutes, you make an 800 SAT. Okay. I mean, seriously, you will get it. The reason I'm doing this is these are pitfalls people fall into them all the time. And I find out about them too late. So I'm trying to anticipate you a little bit this time. Okay. I cannot assume that you know pre-calculus. I can assume that your algebra is pretty good. Just for basic experience. I can't assume that you remember much about linear algebra, but it comes back to you. So you do remember something. Okay. That depends. Some people just really understand it, really do well, retaining it. Okay. Let me ask you one thing that's important here. How many of you can tell me how to find the average value of a function? Just raise your hand if you think you know. You remember seeing it in calculus 1 or 2? Average value of a function. Okay. Hang on a minute. We got one. Okay, so the derivative of this function, which isn't incidentally quite the right function, but I wanted to keep it simple and show you that, well, you'll see in a minute. So what's the derivative? Well, the derivative of t squared is 2t, so it's a times 2t. And the derivative of t is 1, so I could say it's b times 1 plus 0 if you want to write out every step, which is a good idea to reinforce exactly what it is you're doing. Okay. So that would be 2at plus b. Some people left the 2 off there, some people left the B off. Most people had the general idea. So you're gonna get a little bit more up to speed, but nobody's gonna have any problem if you do that, okay? So that's not a problem. That won't be a problem. Okay, now here's another one. Um, deciding how I want to write this. I'm going to write omega sub 0, which means just a constant, okay? Just some number like our initial value of omega. It's like, well, what omega is how fast I got this in rotating at first. So at the instant my finger left the beam, that would be like your initial velocity if you start your time at that point. It's a value of omega when t equals 0, okay? Okay, so what's the integral? Of omega of p with respect to time? Go ahead and write that down. We'll take a look. Okay, now I've switched notations here just a little bit. That thing there is an alpha. You familiar with the Greek alphabet? Alpha, beta, gamma, delta? At least, there's, I forget what upsilon looks like because I haven't used it in a while. Okay. So you don't have to know the whole Greek alphabet, but epsilon, delta, stuff like that. Okay. You've seen some of it. Okay, this is omega naught. Okay. And the antiderivative of omega naught, well, omega naught t has derivative omega naught, right? So when you integrate a constant with respect to t, you're going to get that constant times t. Well, that's going to come back to you quickly. And then you're going to have I'll write it as alpha times 1/2 t squared because t squared is 1/2 t squared has derivative t, right? Most of you got that. Some people didn't see my alpha right, but that's not an issue at all. And then it's plus an integration constant. I didn't see that in anybody's paper. That integration constant is very important. Okay. Okay. So that then would be okay. Well, doesn't that have the same form as this? I got a 1/2 alpha t squared. Well, I've got an a t squared here. Okay. But let's make that what it should have been. It should have been 1/2 alpha. That's like alpha t plus b. Now that's a derivative of your theta function, your angle as a function of time. This is your angular velocity as a function of time. Okay. Now, if theta is in radians, which is the default measure of angular position, sometimes you would want to use degrees, it'd be okay. Sometimes you use revolutions. Just make sure you know what you're using by writing it down. Okay, so theta in radians if theta is in radians, what are the units of omega? Well, at this point now, theta prime of t is omega. So omega is the rate of change of theta. It's the rate of change of your regular position. Okay. Now, if omega is the rate of change of theta with respect to time, what are the units of omega? Okay, well, theta is d theta, omega is d theta dt, right? That means you're taking an infinitesimal change in theta, which would have units of what? The change, well, theta is in radians, so change of theta is in radians, divided by an infinitesimal increment of time, which is seconds, so it's radians over seconds. That makes sense. Okay. That makes sense. Can you read it? If you can't read it, you might want to move closer, plenty room closer. Because I try not to write too much smaller or sloppier than that. But that's about what it gets. Okay. All right, so the other thing is then, what are the units of alpha? Well, I'm going to work it out for you. There's some other things we want to do. Okay. So let's just think. At 1/2 alpha t squared must have units of what? Anybody feel like they can answer? Don't answer, I'll pause it. And then perfectly willing to walk over there and hit a button for an answer. Anybody have an answer? What are the units of 1/2 alpha t squared, which appears right here? What do units that have to be? Okay, well, let's see here. Actually, there's an extra step in reasoning that out. Because I haven't really said what this is, but what this is this, right? So I could say theta of t is the integral of omega of t because omega of t is the derivative of theta of t, right? Here's your theta, here's your derivative. Here's the integral of that derivative, which is back to the same thing you started with. It's the antiderivative, right? So theta derivative, omega antiderivative, okay? So let's just, whether you totally understand what I just said or not, the video is going to get posted. You can replay that part. 1/2 alpha t squared must have units of have to have the units of theta of t because theta of t is a sum of 3 terms. Each of those terms has to have the same units or you can't add them. Okay? I mean, you can't add miles to kilograms. You can't add meters per second to meters per second squared. Okay? You have to have the same blame units. Now you can add radians to degrees, but you got to put them in the same units. Either multiply your radians by 360, sorry, your radians by 180 over pi. But yeah, you got to, just like a common denominator, you got to have the same units. It's not exactly the same thing as a common denominator, but it has a similar feel. Okay, so here we have three terms, all of which have to have units of radians because this is a derivative of this. This, therefore, is an antiderivative of this, which is equal to that. Okay, so that has to have units of radians so that the units of the units of 1/2 alpha t squared are the units of alpha multiplied by the units of t squared. That makes sense? Because the units of that, you know. I'll say that engineers tend not to be as rigorous as they could be with units. Okay, engineers in general, engineering students even more so. You know what the units are supposed to be, so you just fudge it. Okay. And that gets it done, get your grade. Okay. But eventually it'll bite you. So for engineering and for physics, make sure you're a little more tuned into units than I usually see. Okay, units of alpha times units of t squared. The units of alpha times second squared give you radians, right? Has to be if this is going to have units of radians. Alpha is going to have to be whatever you multiply by second squared in order to get radians. You can think about it like that. You want to get used to thinking like that. It's not going to happen instantaneously, but should happen over the next few days. Okay? Make sense? So right there is a simple equation. Units of alpha times second squared is radians. I've written that a little small. I just say units of alpha are radians over second squared, which we can read as radians per second squared. And the camera isn't low enough. There. Yeah, now it's too low. I could adjust that. Okay. Okay, any question on that? I mean, you have the general idea. And the general idea that units are really important. Okay. Kind of essential for understanding. The units can often lead you to the right equation or the right relationship. Okay. It's still got to be careful. Okay. Well, now I'm going to stop talking about this because I've talked a little bit about the kind of calculus you got to be able to do. And you're either there or you're, just that far from it. So make sure you make that transition. Review how to do derivatives of polynomials and trigonometric functions. Okay. Especially sines and cosines. And with a little chain rule. Like what's the derivative of sine of 3t? What's the derivative of sine of 5 pi t? You got a little chain rule. So very easy application of chain rule, but got to be able to do it. You should also, product and quotient rule are going to be important, but not with arctangents of exponentials and stuff like that. Okay, so talking a little bit about the course, and I'll raise the camera so I can look you in the eye because my eyes are right about here where the camera's about here. Okay, well, I apologize for the view, but there I am. Okay, first of all, this course is calculus based. I don't see any sign among what you've done that with just a little review, the calculus will come back to you. I am going to ask you to do one thing. Come in here next time, make yourself a note of this. Come in here next time knowing how to find the average value of a function. And even to that extent, I'm going to write just a little more, make sure that I'm on visible part of the board. Consider that to be a homework problem. And work the thing out. Do not ask AI to solve it for you and tell me that you've solved it. Okay? That's for your own sake. I won't know the difference. Actually, if it's done in really precise mathematical style, I might suspect it, but I'm not going to worry about that. You need to worry about it. Okay? Now, if you know the definition of average value, then that's a really easy question. So you might ask AI if you want, or you might go to a book and ask and go back to your calculus book. Probably best to go back to your calculus book if you got one, because it automatically, by locating it in the calculus book, you know what else it's related to. Because you just want to go to AI and ask it. Okay. If you do, you might want to ask AI, say, oh, gee, I don't understand that. Now, I've had a calculus course, but it's been a while, like 5 months. And I've forgotten it. Can you explain it to me? Not how to get it, but what it means and why it is. Okay? Because it's an important concept that you will need in this course. First of all, how to do it. That's the first step. That takes you a good ways. Second, why does it work? Because then you have more insight into how it will apply to this physical or engineering system. Okay? So come in with the idea of average value as nailed as you can get it in, say, 30 minutes. Okay? Give yourself 30 minutes. You at least know how to do it. You just know, be able to answer that question in 30 minutes, but dive into it a little more deeply than just how to answer this one question. And that gives you a little hint as how you might use AI in this course, as opposed to using it to find answers to homework questions so you can get the 5% of your grade that you get from homework and make 12% on the test from not learning anything by doing that. You understand what I'm saying? I don't think you're going to do that. Y'all have gone through, most of you, everybody's gotten through at least a Calculus 1 course, okay? And most of you have gotten through some engineering courses. So you're not stupid. So don't act like you're stupid and use AI to do your homework, okay? You can ask AI how to explain this concept. You say, I'm a first year physics student. I'm a little confused in a few things. Can you give me a nice general explanation of this concept? Okay, that was a good explanation. Now, can you, I got that. Can you give me a little more meaty explanation? Okay, that was too meaty, but I'm happy with what I got. All right. That's totally valid. But type in a homework problem, get the answer and turn it in. You're doomed. I'm sorry. You're doomed. Okay. So don't be doomed. If you've got a problem, yeah, of course, you can always email me a question too, or stop by. Okay. Okay, the course. You're going to have homework. You're going to come into class. And you're going to have a quiz over your recent homework. Maybe the homework you just did, maybe the homework you did a couple of days ago. Or maybe something earlier that I just want to reinforce that I find people lost track of. Okay. The homework itself, you're going to write out on a piece of paper, and you're going to email me a PDF. Okay. Because I don't want you to have to hand in your paper. First place, you might have it in a notebook. Why tear up your notebook? Send me a PDF. Okay, I'll print it out. I'll have a copy. Okay. I might print it out twice. And one of the copies, make some notes and hand it back to you. Okay. I can even edit that PDF, but that's kind of a pain. It's quicker to write notes. But sometimes I want to make a statement that I have to make in several papers, and I'll go to that trouble. I don't mind the trouble, it's the time, because I've got to balance time and I've still got to unpack this plain layout. Took me 6 weeks to pack it. I think I've got most everything I need for the first half of this course, because I took it to a different place. I didn't let them take it into storage. But I don't have shelves back there. I've just got 60 boxes. So the lab will eventually take shape. I'm going to make it a policy to keep the tables clear though. Okay. And not let the periphery get any more complicated than it is. I'm going to whine for a minute. I was at the gym doing some decline presses. I got to the end and I said, I know I'm not going to be able to get one more, but I'm really going to see how far I can push it, because I usually do. And this shoulder just disintegrated on me. Now that was 8 days ago and it's not that disintegrated. If I do the wrong thing, like if I unbutton this shirt and roll that shoulder like I roll it to get the sleeve off, that crippled me for the day yesterday. They're weird things. So I'm not going to handle those boxes for a few days. I handled them all last week after the injury. I knew what I could do and what I couldn't. So it's going to take me a little while to unpack. Okay, well, that's just, first place. When you're approaching 40 years old, don't try that extra. And when you're almost double that, really, start acting smart. Okay. Not lifting that much weight anymore. Anyhow, why did I have to do that? And take an analogy and be smart in the things you do in this course. Make some analogies. I was stupid when I did that. You're going to do stupid things, but try not to do too many. Okay, because you're not stupid. Okay, now where in the heck was I? You're going to have a quiz. Okay, and it's going to be 10% of your grade. And most of the rest of your grades are going to be labs, which will be about 20% of your grade. And tests, which is the other 65%. Tests are broken down. I'll give you the breakdown. If you've read the syllabus as I recommended, you can see that. There are a lot of specific objectives. Yeah, it helps to read those, but you can kind of scan them because you won't know what most of them mean. And that's most of it. I'm not going to print that out for you, but I think I'll print out the rest. You have it. Okay. You see how the grading is. Typically, there'll be 3 tests, one fairly early. It counts. It's weighted as 1. If you do well on it, it's weighted as 2. Okay, it counts double. Okay, you have a midterm, which will count like 2. Okay, and the final will count 2 or 4. And I think the numbers are a little different, but there's the idea. Final counts most. Okay. Danger of D, but we'll see. In the final will generally be one of the things I look at to see whether I give you a boost. Okay. I like to give you a boost if I can, if you're fairly close. Also, I want to make sure they don't boost you over somebody who hasn't done who has done as well. Okay. Yeah. Make sure that the grade's in the right order. So I do those things with grades. I make comparisons. Okay, here are my A's, here are my B's, here are my C's. Now, documenting, of course, by documentation and everything, is that fair? There are only 7 of you here, 6 of you, can't count. 1, 2, 6, yeah. Make sure that somebody that got a C didn't do better or as good as somebody that got a B. My grandson took this course a few years ago. He's in the 2nd year as an engineer at Norfolk Naval. Pretty bright guy. Did well in my course. He made an A. He told me I didn't deserve that A. I said, yeah, you didn't. But you beat this other guy who did deserve the A. So I had to give the A, and it killed me to do that. You understand what I'm talking about, right? So you'll see more about everything we're into next time. Labs will typically meet on alternate Fridays. And we usually meet from either 10 to 1 or 11 to 2, depending what works better for people. So next time we will talk about that, about whether we want to have a lab this Friday. I'm inclined not to have a lab this Friday, just because of the unpacking situation. And the fact that we'll probably do some observations in class next time, and even Monday. Well, we're not going to do any observations Monday because you're not here. And some lab related stuff that fits right into this whole scheme. So make sure you review this. There's a transcript. I'm noticing that the transcripts we get on YouTube videos are pretty good. Don't always have time to edit those. But I'll do my best to read through them, make sure that all the words are right. But, I've been impressed. When they first started using AI to do transcripts, it got much worse. It was pretty good in 2012. In 2018, it all of a sudden really sucked. It was really bad because they're using AI before they had any business using AI. Scripts are going to be pretty good. Then you can, if you want to remember, put them in your notes or just make notes. If you understood everything, you can just look at the video, just fast forward to the next thing I wrote on the board or the next board before I took everything off. There's only really one board this time. And you can pretty much see everything I did if you didn't write it down. Okay, so use it if it's helpful to you. Textbook, we are officially using the OpenStax textbook. It's online. It's easy. If you want to buy a printed copy, it's only about $50. You buy it from OpenStax. Some people do that because you like that. I think a physical book is a good idea, but that's what I grew up with. Some people prefer the online. And there's a PDF that you can just keep permanently on your device. Your device does that. I don't know. I don't use smartphones. They're too slow. Okay. And my thumbs have better things to do than type because I type much faster with my fingers. I never lost my train of thought because I haven't eaten for 4 hours. And I try to eat something between classes so that doesn't happen. What was I just, it doesn't matter. You know, there are 10,000 people, 40 or 50 people look at these videos. So I can't monitor where they came from. YouTube used to do that. And people in outer Mongolia using my videos. I think those people probably regretted it since then. Okay. Okay, so I'm just going to stop the video here, see if there are any questions.